Astrophysics and Cosmology questions. Last we discussed was question 21. Then we have question 22. Question 22. Hertzsprung-Russell diagram shows the luminosity varies with the surface temperature for the range of the star. The sun is a yellow main sequence star. The position of the sun in the diagram is marked with S. Complete the temperature scale for a Hertzsprung-Russell diagram. So remember Hertzsprung-Russell diagram, the temperature scales are always in division. Like example, if this is 6,000, so and it's always decreasing. 6,000, so half of 6,000 will be 3,000. And this will be double. Double of 6,000 will be 12,000. And this will be double of 12,000, which is 24,000. That's how the scale, the variation is there. But we just have to number the two lines, complete the temperature scale on the Hertzsprung diagram. So that's how we complete it. In part B, compared with the sun, white dwarf stars have a lower luminosity and produce a whiter light. Like when we compare with the sun, the white dwarfs have a lower luminosity. They are not that luminous and produce whiter light. It is not possible to directly measure the size of these stars due to their large distance from the Earth. Explain how astronomers have deduced that these stars have a relatively small surface area compared to that of a sun. Like how astronomers are sure that these white dwarfs, their size is much smaller as compared to that of the sun. So normally what we do, we record the spectrum from the star. That is how, so like let's say this is a white dwarf, and from a white dwarf we record the spectrum because it is emitting out different radiations. And that spectrum will have a wavelength is there, and it can be a luminosity or it can be intensity as well, the graph. So we will have the wavelength, the intensity, like the wavelength at which intensity is maximum, what we call that wavelength, we call lambda max. So what astronomers do, first they determine they focus on the star and record the spectrum or the light emitted from the star. Then after determining finding the lambda max or the maximum wavelength, we know according to Wien's displacement law, the product of a lambda max and the temperature of the star should be 2.89 into 10 to the power minus 3. So they know the lambda max. So they determine the temperature of the star. How they determine temperature of star? Because like 2.898 exponent minus 3 divided by lambda max. They knows the temperature of the star. Like what is the specific temperature of the star? Now we know the temperature of the star. Now we know the temperature of the star. So what we can do, we can use the Hertzsprung-Russell diagram, which is a HR diagram. The HR diagram is a comparison between the luminosity and the temperature. The temperature scale is there, but that is in decreasing. And here's the luminosity. So this will be the Hertzsprung-Russell diagram. So using the Hertzsprung-Russell diagram, once we know the temperature of the star, like what is the specific temperature of the star, we'll find what is the luminosity of the star. Okay. And then Usually, because in what is the general trend, if the star is having a low luminosity, it will have a smaller size as well. That's a relation between luminosity and area, according to the Stephen Boltzmann law. That if a star is having a large surface area, it will be more luminous. So these are the parameters which we use. So what we did explain how astronomers can deduce that these stars have a relatively smaller surface area compared to that of a sun. So when we work out, like you first we take the spectrum, observe the spectrum from these stars, and from this spectrum we'll determine the maximum wavelength, the peak. Remember, maximum wavelength does not means that it is a highest wavelength. Maximum wavelength means it is a wavelength for which intensity is maximum. Like most of the radiation are in this order. That is the meaning of lambda max. Lambda max does not mean the maximum wavelength. It means it's a wavelength which maximum amount of radiations are coming out. So using a lambda max, we determine temperature, and then using a HR diagram, Hertzsprung-Russell diagram, we determine the luminosity, and the star will have a low luminosity than sun. So it means that it will also have a very small size as well. Is it clear? Question 23. An exoplanet is a planet orbiting a star other than sun. So this is representing an exoplanet. Exoplanet is what it shows. An exoplanet is a planet orbiting a star other than the sun. And so you can see a star and there's an exoplanet. One of the first exoplanets to be found was Top Otis B in the star system. Both of the stars and the exoplanet are in orbit about the point just outside the star. The exoplanet was detected by change in the wavelength of a light received from the star. Because of the circular path of the star, the wavelength light detected from a star changes. Explain why the wavelength of a light detected from a star would change. So what we have to do, we have to determine here a Doppler, because see, the circular and the wavelength which you receive from the star, the exoplanet was detected by change in wavelength of a light received from the star. So how we can determine this? It's a simple Doppler effect is there. And what will happen in a Doppler effect? Like you can see that as the star will move towards or away from the Earth, there will be a change in wavelength. So when the star is moving towards the Earth, the wavelength will appear to be decreased and the frequency increases. And as the star is moving away from the Earth, like let's say we are observing from here. So when this star is moving in this direction, like moving in this, so it's like it's moving towards. So this star might contain hydrogen, most of the star hydrogen and helium, but it should give like 400 nanometer. But what we receive will not be 400 nanometer, it's moving towards. So we receive less than like a smaller wavelength, like let's say 398 nanometer. And when it is going away, like moving away, so as a result, the wavelength, it should give 400 nanometer. Example, this 400, even it's an example, not the exact number, but it should give 400 nanometer, but the wave, as it's moving away, the wavelength appear to be longer, might be 450 nanometer. So the change in the wavelength due to a motion of a star towards or away, what we call that as a Doppler's effect. Is it clear, this one? Next is for a spectral line of a wavelength 622 nanometer, the maximum change. Look here, they give a maximum change. Maximum change means delta lambda is given. The maximum change in wavelength was 9.37. Calculate the speed. So how to determine the speed? So a repeated pattern is there for this type of a question in which we have to determine the speed of the star or the speed of the particles in the star. So or speed of a galaxy. This so we determine the Doppler shift, which is a change in wavelength over original wavelength. So what is the change in the wavelength? As it is written 9.7, it's plus minus. Why it is written plus minus? Because the same amount when it is moving towards the same distance, same speed and going away, but with the same speed, so the change in wavelength, the change will be same. Divided by why I did not convert these units, both are given in nanometer. So I did not convert because I will just take a ratio of them and then if I need Z is equals to C by V. So if I need, Z is equals to V by C, like speed divided by, so we multiply by speed of a light, which is 3 into 10 to the power 8. That will give us the speed at which the star is moving. If one was wavelength was given in meter and another one is a nanometer, then I have to convert the units. But in this case, because I have to just divide, that's why I don't have to convert the units. What's the answer here? 469.2. Okay. So we got 469.2 meters per second. Isn't it 3 exponent 8 is the speed of a light? How does this give us speed again? Because the formula is that the Doppler shift, which is a Z, is the speed of the object divided by speed of the wave. That's a formula of the Doppler shift. So if I need the speed of the object, the Doppler shift multiplied by speed of the wave, because in all these cases, the stars are giving us electromagnetic radiation. So all electromagnetic radiation have a speed of a 3 exponent 8 meters per second. That's why we use this formula. So Doppler shift is actually a ratio between the speed of the object and the speed of the wave. If it was a sound wave, then I'll substitute the speed of a sound. Like the speed of the object will be divided by 3x, like if it's speed of sound to 330, I'll multiply there. But because it is electromagnetic radiation, so I have to use the speed of the electromagnetic radiation. It is a Taubotus is a main sequence star that is more massive than the sun. Explain how the temperature would compare with that of the sun. So it is more massive, like it has a more mass. So what do we expect? So if it's a more massive star, yeah, it will have a, that's right. If it's a more massive star means it will have a more fuel also, like more greater rate of a fusion will be there. You have to compare the relating them. So more massive star means like it will have more fuel for the fusion, or it will also have a greater gravitational force. So greater rate of the fusion or the temperature of the star will be higher. If the temperature of the star will be higher, so we expect that it will also have a greater luminosity. Here we have to compare temperature. That's fine. It will be higher, but it's a 3 marks. So you have to relate them. So it means A massive star means it has more fuel for the fusion and stronger gravity, which results in greater rate of fusion, release more energy, and increase the temperature. So we expect it will have a high temperature compared to that of sun. That we'll write the last statement. The next is the exoplanet has more mass than 4 times the mass of a Jupiter. Suggests why much less massive exoplanet are much harder to detect by measuring a change in a wavelength of a light. It's the same question. Look, if they said like less massive exoplanets are harder to detect as compared to massive exoplanets. So what is the reason for that? Because if it will have a less mass of an exoplanet, so it will have a smaller gravitational force on the star. So as it will have a smaller gravitational force on the star, the the change in the orbit, like example, the position of the star will very small change will be there. Like if you see this question compares this question with the question which we just discussed previously, like yeah. See, this is the same question actually. The massive planet orbit the red dwarf star. So there's a red dwarf star was there, and there's a massive planet. Because of the gravity of this star, gravity of this planet, the star also is the particles in the star also moves. So as a result, when we are observing, if the particles are moving towards us, we observe a shorter wavelength. If the particles are moving away, we observe a longer wavelength. But they are saying if we have like a star exoplanet is there, but which is having a low mass. So as a result, this change in the wavelength will be difficult to detect. So why this change in the wavelength will be difficult to detect? Because if an exoplanet is having a low mass, so it will have a weaker gravity. When it is having a weaker gravity, so it will cause a smaller change in the position of the star. Like here, because of this massive exoplanet, let this a star particles are moving this way. But if it was a smaller exoplanet, so this might be the loop in which the particles are moving. So as a result, very small change might occur, which might be difficult to detect. So when we have a less massive exoplanets are there, they have a weaker gravity because they have less mass. So as a result, the change in the wavelength will be very small, or we may not be able to detect that. But if it's a massive exoplanet, then this change might be greater. So we can easily determine that the star is either moving towards or away. Is it clear? This concept? Any doubt in this? No, the gravity of the planet is affecting the star. Like, say, this is our sun. So, this is our sun, and there is a massive planet in our solar system. If there is a massive planet in this, that is so what we call what is the effect of this planet that this there's a both are attracting but the stronger gravitational force for the high mass stars means the planets with massive planets. So as a result, what will happen? The star particles in the star might start to move towards the planet slightly. It's not like too big, but yes, it does, some of the particle move. So this is caused by the planet, the massive planet. If it's a minor planet, then this change will be there, might be very small, or may not be able to detect that change. So the movement of the star, because of the planet, the stronger gravitational force of a planet, we call that as exoplanet. So by the help of these exoplanets, we are able to determine the different stars, we are able to determine them. We have question 24. The sun is a typical star in our galaxy. This is our Milky Way galaxy, the spiral arms you can see. The center of a galaxy, we have black central black hole is there, which is holding these all interstellar bodies in tech. The Milky Way galaxy, it is 2.5 exponent 20 meters from a center, and the sun orbits the center with a speed of 220 kilometers per second. So sun is also moving relative to the center. The sun is also moving. So the speed is 220 kilometer per second, and the distance is 2.5 exponent 20. The diagram below represent a Milky Way. The central black appear like the central black area represent a very dense, very high density star, which is also known as the nucleus of the galaxy. The total mass of the star within the orbit of the sun may be treated as a point mass. Like we can compare, so many particles are there, but we consider them as a point mass, like all together. And the sun may be treated as a point mass at the center. So we can also treat our sun. Now the question is, calculate the mass of a Milky Way within the orbit of the sun. How much mass is there within this orbit? That is what we have to determine. So how to work out the mass of the Milky Way? Look, what we are considering, we will consider the Newton's law of gravitation. According to Newton's law of gravitation, the Newton, like this mass is pulling the sun. So there is a force of a gravity on the sun, and that force of a gravity is also a centripetal force. So what we'll say the gravitational force is equal to centripetal force. So this whole mass we consider as m, okay? Because they mention here the total mass of a star within the orbit. So this whole mass we call m, and this is the mass of the sun. And this whole total mass we call that as m. So according to Newton's law of gravitation, the force of attraction between the 2 point masses is a product of the mass and inversely proportional to square of distance between them. So I can say the mass of whole like total mass of a star within the orbit, mass of a sun, and divide by distance square, radius square. And centripetal force is mv square over r. So the centripetal force is a force which is acting on the sun as it is moving around. So m mass of a sun, v is the speed square divided by r. Now we simplify this. R will cancel with this. Mass of a sun will cancel with mass of a sun. So what we are left with? We are left with gm over r is equals to v square. If we need the mass, like this m we need, so this will be equals to v square into r divided by g. V is the speed at which the sun was moving. What was the speed? It was 220 kilometers per second. That's the speed of the. G is a gravitational constant. According to Newton's law of gravitation, when we have two masses and their centers are separated by distance r, The mass m1 and m2 are there, so force between them is given by a formula G m1 m2 over r square. G is called a gravitational constant. It is a fixed value. It will be given in exam. So V is 220, but kilometer per second. So 220 multiplied by 1000 square multiplied by radius, which is 2.5 exponent 20, divided by G. So G is a gravitational constant. It will be there as a constant value. It is 6.67 into 10 to the power minus 11. When you substitute, you will get the answer for the mass which is present within this orbit of the sun, that we call that as M, capital M. Is it clear? One 1.8 exponent 41 kg. Yeah, right. So 1.8 exponent 41 kilogram is the mass total which is present within the orbit of the sun. The next is the vast majority of the stars in the Milky Way are observed to be within the nucleus of the galaxy. Like most of the stars which we observe are in the nucleus of the Milky Way. Explain why it might be expected that the star of a similar to the sun but further away from the center of a galaxy would orbit at a lower speed than the sun. Like, so most of the masses here, they're saying if there's another star which is a greater distance from the center of the Milky Way, center of the nucleus of the galaxy, might move at a lower speed as compared to that of sun. Like sun is moving at 220, but that star will move slower. Look, the centripetal force is depending on mv square over r. Okay, m is same for all, like even for sun or for any other star which is far. So m is not changing. But what will happen to the centripetal force? The distance is increasing because it has to experience, whenever object want to move in a circular path, it has to experience a centripetal force, which is F. So F is mv square over r. M is a mass of the stars, like which we consider within the nucleus. That is not changing. What happened to the r? R is increasing, because if you compare this one, this r is greater than this. So r is increasing. So if r is increasing, the centripetal force, because if you compare the centripetal force and r is equals to v square, considering m is constant, m is not changing. So as the radius is decreasing, like radius is increasing, so what should happen to the velocity? Because the centripetal force depending on the distance of the star from us, and this centripetal force is also equals to gravitational force as well, which we like. Mass of a star stays constant. So increase in r, as we increase the r, what will happen to v? If r is increasing, what should happen to the v? The v should decrease. Why v should decrease? So that the force vary with the distance according to inverse square, because the force between the two masses according to Newton's law of gravitation is g m1 m2 over r square. So it means the variation of this force should be equals to, in follow, like if the masses are constant, if the distance is double, the force will decrease by 4. If a distance is 3 times, the force will decrease by 9. And this force is also equals to centripetal force. This is a gravitational force which follow inverse square law, and this gravitational force will be a centripetal force, which is mv square over r. So here what is happening? M is not changing. R is increasing. So if R is increasing, If r is increasing or multiplied, so this should divide it by 4. But here, this is not r squared, this is r. So if this is r, so what should happen to v? The velocity should also decrease. This is one way of answering. Is it clear? Another one, you can use a conservation of energy. The total energy should be conserved. The kinetic plus potential should be same for the two stars. The star which is closer will have a smaller potential, so it will have more kinetic. That's why it is moving faster. But the other star which is further from the nucleus of the galaxy, it's having a greater potential, so it will have a smaller kinetic or moves slower. Is it clear this part? Any doubt in this? Next, we have a star similar to that of a sun, but further away from the center of a galaxy, actually observed to have orbital speed approximately same as the sun. Why astronomers? What astronomers can conclude from this observation? Like practically, we observe some like what should, according to theory, what should happen if the sun is moving at 220 kilometer per second? Another star which is further from the center should move at a lower speed, might be 200 kilometer per second. But practically, it is found that both are moving at the same speed of 220 kilometer per second. So, what could be the reason for that? The reason is like what we calculated the mass, maybe that mass is not correct. There might be a dark matter, like the matter which we cannot observe, we call dark matter. So there might be a dark matter. Because of the presence of the dark matter, what might happen? The speed at which this object is, like according to theory, if the mass is constant, those objects which are closer to the star are moving slower, faster, I mean, and those which are away, they are moving slower. That is a concept. Like that is right thing. But what might happen that when we observe the two objects are moving at the same speed, even if it is further or even it is closer, they're moving at the same speed. So what we can conclude from this, like what astronomers can conclude from this, so it means the mass which we calculated or they calculated might be greater than the expected mass. Because if the mass is more, stronger gravity is there, or there might be an additional matter which we cannot observe, or there must be a dark matter, because a dark matter is responsible for keeping the things together and moving at different speed. So because of the existence of the dark matter, which is not, we are not able to observe directly, so the mass, the mass of a galaxy might is greater than the what we expect. That's why it is causing the both stars to move at the same speed. Is it clear? So these are the questions: astrophysics and cosmology. I have already shared all these exercises with you. You can solve and submit.